Okay, so if everybody can hear me, we're going to start with atoms, and we're going to review the structure of an atom, and then we're going to talk about trends in the periodic table. We're going to review all the stuff that's been in the module since distance learning started. Hope everybody's doing well and everybody's safe, and nobody's going too stir crazy. Okay, let's see how well this is going to work. All right, let's start with an atom. So here we have a simplistic modern view of an atom. So obviously, the modern view of an atom isn't easily transcribed to a 2D page, but this is the best representation that we can have, especially for the introduction to the atom and just starting to understand the concept. But here we have the outside of an atom. So out here we have what you now know to be the valence orbit, or the valence shell. So this is the orbit that contains the outermost electrons. These are the electrons that are in charge of the characteristics of atoms and elements, so the characteristics of bonding and bonding with other atoms to create molecules. And then in here we have the inner shell of electrons. So there's 2 electrons on this shell, and on the outer shell we have 1, 2, 3, 4, 5. So these we have electrons, and electrons are negatively charged particles, so we show them like this, like a symbol. So they have a negative charge on them, which is opposite of the positive charge that we find in the nucleus with the protons. So the nucleus is inside the atom, and this is obviously not to scale. The nucleus is extremely small relative to the size of the atom. In fact, if the atom was the size of a football field, this was the entire atom, and these edges would be the valence electrons, the nucleus would actually be about the size of a fly that landed right in the middle of the football field. The scale is enormous. The nucleus is extremely small, and in Rutherford's gold foil experiment, he shot a bunch of alpha particles at a thin sheet of gold foil, and while most of the alpha particles went through the gold foil, in fact over 99% of them did, every once in a while one would shoot back, which told him that there's obviously a hard, dense nucleus inside the atom. However, it's extremely small because it only takes up a very small percentage of the atom's space. So we have the nucleus, and inside the nucleus we have protons, which are positively charged, and neutrons, which actually have no charge at all. So we have protons on the inside, neutrons on the inside, forming the nucleus of the atom, which is hard and dense, and then we have this huge cloud of electrons on the outside. And depending on where the atom is on the periodic table and which atom it is, we'll have different number of orbits and different numbers of electrons in the electron cloud. All right, let's move on to more of a modern view of the atom. So we never really know where an electron is. In fact, when you get into more advanced views of the atom, you'll know that the electrons are never in one particular place. When we talk about orbits, we're actually talking about energy levels of the electrons, and these clouds here represent the different energy levels. So this is the inner energy level, which we're calling the inner orbit, and this is the outer energy level, which we call the outer orbit. We would call this the valence shell. And what this represents is this atom doesn't have thousands of electrons in it. What this picture represents is the fact that an electron cloud can have an electron in any particular part of the cloud at any one time. We don't know where the electrons are. It's just a value of probability. So this is just representing the fact that this is the inner orbit, and the electrons could be anywhere within that orbit. We're not really sure where. And this is the outer orbit, and the electrons can be found anywhere in the outer orbit. We're just not really sure where. So let's talk about the difference between elements and compounds. An element is a single atom. So if we have hydrogen, that's an element. If we have lead, that's an element. If we have helium, That's an element. An element is an individual atom. We can also have element compounds. A compound is something made up of more than one atom. An elemental compound is a molecule made up of more than one of the same type of element. So if we look at some of our diatomic molecules, for example, oxygen is a diatomic molecule. So oxygen doesn't like to exist on its own. You'll never really see oxygen kind of freely by itself. It likes to bond to itself. So it'll bond to another oxygen. So this is still a molecule. It's a molecule because it's made up of more than one atom, but it's an elemental molecule because it's all made up of the same atom. And then we have molecular compounds, which are made up of different types of atoms. So water is the classic example. We'll have H2O, so we'll have two hydrogens, and we'll have an oxygen. So molecules made up of different types of elements. Elemental molecules or elemental compounds made up of more than one atom, but of the same element. And then we have elements which are just individual atoms. Okay, so let's talk about the periodic table. There was a lot of confusion about the periodic table and the periodic trends, so it's something that we are going to revisit because this is really important and this is definitely something you're going to see in grade 10. In fact, in grade 10 chemistry, you spend most of your time talking about the periodic table and the bonding affinities of different elements and the different types of bonds. So it's important, even through distance ed, we obviously can't go through the whole material, because we're going to have to scale it back just due to the restrictions of distance education. But one of the things that I really want you to take forward into grade 10 is a concept of the trends in the periodic table, because that's really, really going to help you out next year. All right. Here we have the periodic table. And we have different groups and we have different periods in the periodic table. And every square represents a different element. The very first one is hydrogen. Hydrogen is the most abundant element in the universe. It's also the easiest to create because it only has one proton and it has one electron. In fact, there is a correlation between the atomic number, so how big an atom is, and how difficult it is to make. These grayed out ones down here on the periodic table are actually atoms that we haven't discovered but have been theorized to exist, or some of them have been made in a lab, but none of them have been found in nature, because the larger the atom, the larger the star needed to create those atoms. And atoms, most of these atoms, except for the very first few, so as we start getting past these atoms here, all of these atoms here were created in supernova. They're created when stars explode and the energies are so intense that you have fusion, which is the combining of atoms into larger atoms. And so the larger an atom is, the larger the supernova needed to create that atom. And so these atoms down here are only really created in very, very large, massive stars, and the death of those stars. And because they're not as common, we don't really see those elements. And just because the elements haven't been found in nature on Earth doesn't mean they don't exist. It just means they're probably so rare that we just haven't come across them yet. So here we have hydrogen, which is the easiest one to make. This is an atom that has one proton in its nucleus and one electron out in its orbit. The simplest of atoms. And as we move forward, so helium, we'll have 2 electrons, 2 proteins, lithium, beryllium, and as we increase the number of protons, electrons, and neutrons in an atom, we're actually making the atom larger. So the further down we go on the periodic table, as we go in this direction, we generally get larger atoms down here. Okay, so I think we need to talk about what is represented in each box of the periodic table. So here's fluorine, for example. Fluorine is halogen, so fluorine's right here. Fluorine is very reactive, and we'll talk about why, but it's basically because it's missing a full valence shell by one electron. It just needs one electron to obtain a full valence shell, and it's very aggressive in gaining that one electron. So here we have a box that represents an element in the periodic table, and every periodic table is going to have a different look. So every periodic table's box will look a little bit different. The atomic number will be in a different place, the ionic charge will be in a different place, but generally this is going to be the format. So right here, right in the middle will be the element, and also known as the atomic symbol. So this is the short form for the element. Obviously, as scientists, we're pretty lazy, and we don't like to write out fluorine every time, so in scientific papers and in textbooks, you're just going to see F. And then we have the number at the top left. This number here represents the atomic number. And the atomic number is where it lands on the periodic table. So hydrogen has an atomic number of 1. This is the first atom. Helium has an atomic number of 2. Lithium has an atomic number of 3, beryllium 4, boron 5, carbon 6, 7, 8, 9, 10, and then we start again here, 11, 12, 13, 14, 15, 16, 17, 18, and so on and so forth. There's a big gap here because we group elements according to their characteristics, and nothing really fit here. So we created a gap. So we just skip. So we go from 4 to 5, 6, 7, and there's gaps here until we get to the fourth period here, in which we have 18 atoms across the row. So that's the atomic number. The atomic number also represents the number of protons, because every successive element has 1 proton more than the element that came before. So if we look at hydrogen, hydrogen has 1 single proton, 1. Helium has 2. Lithium has 3, beryllium has 4, boron has 5, 6, 7, 8, 9, 10, and that was a major characteristic that helped us to put these atoms in order. So each atom in line in the periodic table has 1 more proton than the one that came before. So the proton number, or the number of protons in the nucleus, and the atomic number are exactly the same. So if the atomic number is 9, fluorine is the 9th atom on the periodic table, it also has 9 protons. All right, down here we have the atomic mass. And atomic mass is measured in atomic units. Atomic units are a mass that we had to invent for the discussion of atoms and molecules, because atoms and molecules are so small and subatomic particles weigh so little that we really didn't have anything in terms of scale that could easily represent the mass of subatomic particles. So we just said, look, if we have protons and neutrons in the nucleus, so we have protons and neutrons in the nucleus, and then we have electrons on the outside. Protons and neutrons pretty much weigh the same thing, so we're going to say each of these weighs 1 atomic unit, because that makes it easy. So a single proton is 1 atomic unit, and a neutron is 1 atomic unit. So if we had 2 protons and 1 neutron in the nucleus, this would be a total of 3 atomic units in mass. Electrons, while they do have a very, very small mass, it's so incredibly small that we basically consider them massless. So we basically say it has no mass. because relative to the mass of protons and neutrons, it's so incredibly small that it really doesn't really matter for our discussions. So atomic mass is how much the atom weighs. And if electrons aren't contributing to the mass of the electron or to the mass of the atom, the only other subatomic particles that are contributing to the mass of the atom are the proton and the neutron. So if this is the total mass, then 19 atomic units, so 19 atomic units is equal to the mass of the protons plus the mass of the neutrons. And because one proton is equal to one atomic unit, if the atomic mass is 19 atomic units, then I know there's 19 protons and neutrons total in the nucleus. So if the atomic mass is 19, then I know that the number of protons plus the number of neutrons is equal to 19. And I already know how many neutrons there are, or protons, sorry. I know how many protons there are because there's already 9 protons in the atom as told to me by the atomic number. So I already have 9 protons. Well, if I know how many protons there are and I know what the total mass is, I can figure out how many neutrons there are. So if there's a total atomic mass of 19, there's 9 proteins, this number here must be 10. So therefore there are 10 neutrons in the fluorine atom. There are 9 protons. And in a non-ionic atom, there are always the same number of protons as there are electrons because they like to balance themselves out. And because electrons have a negative charge of 1 and protons have a positive charge of 1, neutral atoms need to have the same number of protons as electrons so that the charge is balanced. So if I have 9 protons in the fluorine atom, I would also have 9 electrons in the fluorine atom. Okay. So let's explore in more detail the first 20 atoms on the periodic table. So now that we know a bit about how the patterning of the periodic table works, we know that each successive atom has 1 more proton and 1 more electron than the one that came before. The number of neutrons doesn't really follow that pattern. The number of neutrons sometimes skips atoms, so you kind of have to pay attention to the actual atomic mass to see how many neutrons there are going to be in any particular atom. And a good example of that is hydrogen. Hydrogen has an atomic number of 1, so there's 1 proton, but it also has an atomic mass of 1, which means it has 1 proton and then it has 1 electron to balance that proton. But then if the mass is 1 and there's 1 proton, that means there has to be 0 neutrons. And there's no neutrons in a hydrogen atom. You find your first neutron as we go up the periodic table. So we do have to be careful and make sure we use the atomic mass to calculate the number of neutrons in a particular atom. Okay, so let's explore more detail. The first 20 atoms of the periodic table. All right. Perfect. Right. So we've already talked about hydrogen. So let's plug that in right now. Hydrogen, and it is the very first, the easiest to make, the smallest of the atoms, and it has an atomic mass of 1, which means it has a nucleus made up of 1 proton. So let's actually list that. Let's say that this has 1 proton, and outside it has 1 electron. It has 1 electron. All right, and then we have helium. Helium has 2 protons, so we have 2 protons in the nucleus, and its atomic mass is actually 4. So it has an atomic mass of 4, which means that there are 2 protons, but an atomic mass of 4, then it must have 2 neutrons. So it has 2 neutrons, 2 protons, and to balance those 2 protons, it also has 2 electrons. And we'll draw one here and one here. And that's on the very first orbit. Now, the very first orbit of an atom can only fit 2 electrons. So we can only have on the first shell, we can only have 2 electrons max, and that's it. So these are full. As soon as we have helium done, we can't fit any more electrons on that orbit. But the third element, lithium, has 3 electrons because it has 3 protons. So we need another place to put that third electron. And what happens is we'll have the first orbit with 2 electrons, and then we'll have another orbit with that extra third electron. So this is atomic number 3. This is going to be lithium. It has 3 protons. Lithium has an atomic mass of 6.94. We round that to 7. So it has an atomic mass of 7. It has 3 protons, so it must have 4 neutrons. And in its inner orbit, it has 2 electrons, but I know it has to have 3 electrons total because it has 3 positive protons and it needs 3 negative electrons to balance that out. So we're going to add another orbit. This is going to be its second orbit or its second shell. And we're going to put 1 electron on that next orbit. Now that second shell can fit more than 2. It can actually fit 8 electrons. And that's why we have 1, 2, 3, 4, 5, 6, 7, 8 elements in the second period. This is a period and this is a group. We have 8 elements in the second period because we have 8 electrons that can fit on that particular valence shell or that particular orbital. All right, so this is lithium. Let's move on to beryllium. So we have beryllium in here, which is Be. Beryllium is the 4th atom on the periodic table, so it has 4 protons. It has an atomic mass of 9. So 4 plus what is equal to 9? Okay, well this must be 5, so I have 5 neutrons. And then I have my inner and my outer orbits or shells. 1 electron here, 1 electron here, 1 electron here, and I need 4 total because there's 4 protons, so I need 4 electrons, so I'm going to put 1 more here. We get the idea. I'll do boron. So let's do boron, and boron has an atomic mass of 10.8. So because it's 10.8, we'll round that to 11. I know that it has 5 protons, so we got 5 protons. It has an atomic mass of 11, so it must have 6 neutrons because 6 plus 5 is 11 atomic units. And then I have my first shell. I'll put my second shell on there too. And I have 2 electrons on the first shell. And then I have 5 protons, so I need 5 electrons. So I'm going to go 1, 2, 3 on this outer shell. So 1, 2, 3, 4, 5 electrons, 5 protons, and the 6 neutrons on my boron atom. Let's skip the next ones because it's kind of the same pattern. We'll get here and we'll have our noble gas, which is neon. Neon is pretty common. It's used in neon signs. It's the gas in neon signs that lights up when there's an electron current flowing through it. It is very stable. It doesn't like to bond. And it's very stable because it has a full valence shell. And we'll talk a bit more about valence shells tomorrow. But this particular atom will have 10 protons because it's atomic number 10. So it's got 10 protons in its nucleus. So we have 10 protons, and it has a atomic mass of 20.1, so we'll round that to 20. So if it's got 10 protons, then it probably has 10 neutrons, and then I'll draw my first orbit, and then I'll draw my outer orbit here. Now, I have 2 electrons on the inner shell, and because I have 10 protons, I need 10 electrons. So we'll have 1, 2, so I have 2 here, so I need 8 on this. Or sorry, I have 2 here, so I need, 8 on this outer shell. So 1, 2, 3, 4, 5, 6, 7, 8. This is the outermost shell of this atom. We also call the outermost shell the valence shell, which contains the valence electrons. The valence shell and the valence electrons are important because it's this outer shell that determines most of the characteristics of the atom, because it's these electrons that are involved in bonding with other atoms. It's the valence electrons that bond and cause bonding and cause reactivity in an atom. So we say that this particular atom, which is neon, so neon is very stable because it has a full valence shell. It can't fit any more electrons on its outer orbit. So it's pretty happy. It's happy because it's got as many electrons as it can possibly get. It's pretty greedy. Atoms want as many electrons as they can fit on their valence shell. They want to be happy. They want to be in a stable form. And neon is very happy because it can only fit 8 on this outside valence shell, and it's got 8, so it's doing fine. And it doesn't like to bond to other atoms because it doesn't need to share or give away electrons at all. So atoms within the noble gases, which is this group here, are very stable and don't like to bond because they all have full valence shells. So let's go down to number 11. Let's talk about sodium. So sodium, we're kind of catching on here, so we kind of get the gist. Sodium has 11 protons because it's atomic number 11. Its atomic mass is 22.9, so we're going to round that to 23. So if it's got 11 protons, then it must have 12 neutrons. And let's draw its first orbit. So if I have 11 protons, I need 11 electrons. I know 2 go on the first orbit. Okay, well, I have a second orbit, so let me draw a second one. Second one, good. I know 2 go on, or 8 go on here, so 1, 2, 3, 4, 5, 6, 7, 8. That's the max I can put on the second orbit. So I have 2 on the first, 8 on the second, I have 10 total, but I need 11 total valence electrons. So where am I going to put that extra one? Well, I'm just going to draw another orbit. And I'm going to plop it right on that outside orbit. And as you can see, it's sort of getting a little cumbersome to start drawing these because they are getting so big. There are many other ways to draw atoms. We're going to talk about the Lewis dot diagrams tomorrow, which is a lot easier because it only shows the valence electrons, which are the important electrons we care about in terms of bonding. So here I have 1, 2, 3 orbits, and the third orbit is the valence shell. So now sodium has a valence shell on its third orbit. And this atom here will also have 3 orbits. This atom here will also have 3 orbits. This atom here will also have 3 orbits, and we'll continue to fill that valence shell. So this atom has 1 electron on its valence shell. Let's see. Yeah. So this atom has 1 electron on its valence shell, this one right here. This atom will have 2. This atom will have 3 electrons on its valence shell. This atom will have 4. This will have 5. This will have 6. This will have 7. And this will have 8. And then we're done. So the third orbit on an atom, or the third shell, can also fit 8 electrons total. And because there's 8 atoms within this period. So the very last atom here is also going to be a noble gas. It's going to be argon, and argon has an atomic number of 18, so it's going to have 18 protons. It has an approximate atomic mass of 40, so it's going to have 22 neutrons, and then it's going to have 18 electrons on its orbits, so it's going to have 2 electrons here, 2 electrons on this one, it's going to have 8 electrons on this one, and then it's going to have 8 electrons on the outer orbit. So all of the electrons in this period have the same number of orbits. They all have 3 orbits. And every electron in the second period all have 2 orbits. Every electron in the first period all have 1 orbit. And that's the pattern of periods within the periodic table, is every single row, all the atoms within that row contain the same number of atoms, or the same number of orbits, or electron orbits. And as you can imagine, these elements down here, this is potassium. Let's clear some of this away to make it a little more manageable. Get rid of all my electrons. Good. This atom down here, which is potassium, is going to have 19 protons. We'll have to figure out the number of neutrons, but it's going to have 4 electron orbits. Everything in this period has 1 electron orbit, everything in this period has 2, everything in this period has 3, and everything in this period has 4. The first orbit will have 2 electrons, the third orbit will have 8. Sorry, the first will have 2, the second will have 8, the third will have 8, and the fourth, which we don't really talk about much in this course, but this one will have a total of, let's see if we can figure it out. Let's go back to our periodic table. So the first period has 2 atoms in it, and so only 2 electrons can fit on the first orbit. The next period has, so this is 2 electrons on that orbit. The next one is 1, 2, 3, 4, 5, 6, 7, 8. So there's only 8 electrons on that shell. And then 1, 2, 3, 4, 5, 6, 7, 8. There's 8 electrons on that shell or orbit. And I might not have mentioned it, but we use the words shell and orbit sort of interchangeably. They all kind of mean the same thing. So on the fourth one, let's see how many electrons we can have on it. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 atoms. So we can have 18 electrons. And the next one has 18 too. We don't really talk much about these in the course, but we are going to focus on the first 3 periods. So I think that's pretty good for a first try at this. We'll talk more about periodic trends tomorrow, but the only other thing I should mention is, and we'll discuss this further tomorrow, but all the atoms within a group, so we know that all the atoms within a period contain the same number of orbits. All the atoms in a group, so all the atoms in a group also share one very important characteristic. So I have, and I'm going to introduce you to Lewis dot diagrams, but we'll talk more about them tomorrow. So this is hydrogen. So hydrogen here, and hydrogen has 1 electron, so we're going to put 1 little electron, 1 little dot on the outside, because it has 1 valence electron on its 1 shell. This is lithium. So actually, let's talk about helium first. So helium has 2 electrons, so we're going to go 1, 2 dots like that. Lithium here, lithium has 3 electrons because it's the third one, so we're going to go, but it has 2 electrons in its first shell, and then only 1 electron on its outer shell. And because it's the outer electrons or valence electrons that are important to us in chemistry, we're only going to show its valence electron. And it only has 1 because it has 2 on the first orbit and then 1 on its second orbit. So it's going to be 1, 2, nope, I'm sorry, 1. It's only got 1 electron on its outer orbit. If we go over to neon, neon has a full valence shell. There's 1, 2, 3, 4, 5, 6, 7, 8 electrons on it. So we're going to draw 1, 2, 3, 4, 5, 6, 7, 8 electrons, like that. Sodium has a new shell. 1, 2, 3. This is the third orbit, and on that third orbit, it is atom number 11. There's 2 electrons on its first orbit, 8 electrons on its second, which means we only have 1 on its third. Argon has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So we're going to draw 8 valence electrons. It is more than 8 electrons, but it only has 8 valence electrons. And you can start to see from the pattern, all these elements in the same group will contain the same number of valence electrons because they each only have 1 electron on their outer shell. They don't have the same number of electrons because potassium, for example, has way more electrons than hydrogen does. Hydrogen only has 1, but they all share the same number of electrons on their valence shell. Just like all the noble gases share the same number of electrons on their valence shell, with the exception of helium. But like most things in chemistry, there's always going to be exceptions. So 8, 8, and they share the same number of valence electrons. This number of valence electrons is 18, so obviously like the system breaks down. So like I said, most things in chemistry have exceptions, and we'll talk more about this tomorrow, but not really. You'll talk more about it in grade 10 and grade 11. But for the most part, what you need to remember about groups is that every group shares the same number of valence electrons, and so their bonding characteristics are the same, and that's why we put them within the same column. I can't answer questions if everybody has questions because somebody just asked me on Teams if I'm going to take up questions. You can ask me questions in the YouTube live chat, actually. So if you navigate to the YouTube window and you have a YouTube channel or a YouTube account, you can actually ask me questions in the YouTube chat. I can see that. But let's see. Hold on. Let me see what questions we have. Okay, welcome back. So unless anybody has any questions, I will end it here. But let me know if this was useful. I'll probably send it to Google form to see what everybody thought, or if it sounded okay, what the quality was like, and if there's anything I can change. But if anybody has any questions, last chance. All right. Well, I hope everybody's safe, and I will see you tomorrow.